Good morning. Welcome to our Science Center talk today. Science Circle, Science Group, whatever, a bunch of scientists. We welcome you to our program. My name is Bob Spiritus. I coordinate this. Our president, Bob Hopper, is off doing something else, so I'm going to run around. I have to do double duty, so I have to make sure that everything's right here. I'll be hopping around. Today we are pleased to have Dr. Barry Taylor present to us. He has PhD in low temperature condensed matter physics from the University of Pennsylvania, and he remained at Penn as an instructor and later as an assistant professor of physics until he joined the RCA laboratory in Princeton, New Jersey as a research scientist. He joined NIST, then the National Bureau of Standards, in 1970 as chief of the Absolute Electrical Measurements Section, served as chief of the NBS Electricity Division starting in 1974, and was manager of the FCDC from 1988 until his retirement. He was the chief editor of the NIST Journal of Research starting in 1988 until he retired. Dr. Taylor has been and continues to be active in several professional, national, and international standardizing committees and has served as the chair of a number of such committees. His current research activities focus on Periodic Committee on Data for Science and Technology, compilations of recommended values of the fundamental physical constants, and on the development and establishment of an improved international system. He's the author of, or co-author of over 100 publications and the recipient of several prizes. Please give a Chautauqua welcome to Dr. Barry Taylor.
Thank you, Bob, and I thank you for... Oh.
If you're out there in Zoom land and have a question, please please send it in through the chat function. Is that right, Larry? Not today. Okay, we're not doing it. Okay, if you're out there in Zoom land, enjoy.
Well, I want to thank Bob for inviting me to give this talk, and the talk starts in 1790 and actually ends in 2019. So I'm going to cover 229 years of activity of how the modern metric system came into being. And there was a major change, as some of you may know, on the 20th of May 2019, and that's where we're headed. Okay, so we start off developing the modern metric system as the title of my talk. I should first often say that the official name of the metric system is actually the International System of Units, SI. But for us who are still in the English-based system, we think about the metric system, call it the metric system. So the importance of weights and measures has long been known, and I have this quote from Leviticus 19, you shall not falsify measures of length, weight, or capacity. You shall have an honest balance, an honest ephah, and an honest hin. No one knows what an ephah and hin are, and that's why in this translation they always use those two words. My guess is one has to do with weight and the other has to do with volume, because those are the kinds of things that people were most interested in back in those days. And it shows you these civilizations have struggled to create practical weights and measure systems for millennia. This is something that goes back thousands of years, actually. First, let me talk about quantities and units. Quantity is not amount of something in physics and chemistry. Quantity is a physical quantity. For example, length. Length is a quantity, and quantities have two kinds of quantities. Quantity in a general sense, like length, mass, time. But then there's quantity in a particular sense, such as the length of a hand span. And a unit is nothing more than an example of a kind of quantity in terms of which the values of other quantities of the same kind can be expressed. So that's an important point. A unit is just a particular kind of quantity. And of course, as a unit, you want a unit should be accessible, not changing, easy to realize. So let's start off 1700s measurement unit chaos in France. They had lots of different units. So life was getting more complicated because of that. And the government asked the French Academy of Sciences to appoint a committee to look into the matter. And the committee came up with a proposal, decimal measurement system based on a universal natural unit. And they chose that unit to be length, a unit of length. And they actually chose a fraction of the 90-degree arc of the Earth's meridian, of all things. And as for the unit of mass, a cube of water with a dimension, a decimal fraction of the unit of length. So this unit of length not only defines length, but also mass, through the mass of a certain cube based on the meter. So the meter was actually defined in French law in the 1790s. 1/10,000th of the distance from the North Pole to the equator along a meridian through Paris. And the kilogram was defined as the mass of 1 cubic decimeter of water at temperature maximum density, about 4 degrees Celsius. And a decimeter is equal to 1/10 of a meter. So those definitions were kind of complicated to realize, so it was decided to actually fabricate artifacts. Platinum meter and a kilogram artifacts fabricated in 1799, and they were made as consistent with these values that were defined, I just spoke about. And they put them in the French National Archives in 1799 and called them the meter of the archives and kilogram of the archives. So in 1799, the metric system was founded, named the metric system. It's based on these artifacts. And they became by law the sole weight and measure systems in France. And the French metric system was subsequently adopted by many countries and copies made of the French artifacts. So we have a metric system based on these two artifacts, the meter of the archives and the kilogram of the archives. Here's a picture of the millimeter and kilogram of the archives. You'll see the meter bar and the kilogram, which is made of platinum. It's about 40 millimeters in diameter and height. Here's a picture of a colleague of mine, Bill Phillips of NIST. He won the Nobel Prize in Physics in 1997, and he's shown here holding the kilogram of the archives. Being a Nobel Prize winner, he was able to. They invited him to go in to see the kilogram of the archives. So there it is. So during the 1800s, commerce is increasing significantly. They decided we need an internationally accepted measurement system needed, even though many countries had adopted this metric system based on the meter and kilogram of the archives. So scientists worldwide were invited to discuss the issue. They had a meeting in Paris in 1875, attended by 30 representatives from various countries, and they signed a document, really a treaty, called the Treaty of the Meter in the United States. Signed it on 20 May 1875 by 17 states, and now there are like 58 member states and 41 associate members. So the Meter Convention establishes three entities: the CGPM, General Conference on Weights and Measures. I should say these acronyms are the French names of these organizations. So the General Conference on Weights and Measures, this is a government treaty. Representatives of the government actually come meet every 4 years. They're the top level decision makers on measurement. The CIPM is an International Committee for Weights and Measures. Generally, they're management level scientists. They meet 1 or 2 times per year. They created the BIPM, the International Bureau of Weights and Measures. It's a laboratory in the Paris suburb. And about 70 current staff. So the Meter Convention actually said officially, meter of the archives and kilogram of the archives, although had been adopted as the basis of the worldwide metric system, they were warned for use because all these different countries are sending their standards to be to France and to be compared. So they decided to make copies. They had a British company make copies, 34 copies of the meter. And number 6 just were chosen randomly was called the International Prototype of the Meter. 43 copies of the kilogram of the archives were made. K3, chosen as the International Prototype of the Kilogram, IPK. So these international prototypes are define the metric system worldwide and were to be kept at the BIPM. So now we have these international prototypes that are the basis of the metric system. Here's a picture from the early 1920s of the BIPM in Paris, outside of Paris, and has added a number of buildings over the years, and was, in essence, given to the to the General Conference on Weights and Measures by the French government. Here's a picture of the international prototypes of the meter and kilogram. These were made of platinum and iridium alloy, 90% platinum, 10% iridium. And you'll notice that this bar, the meter bar, has been made in this particular form so to prevent it from bending easily. And it actually has scratches in this channel. There are scratches, and the meter is defined as the distance between those two scratches. Here's a picture of the international prototype of the kilogram, number K3. It was maintained in a vault and 3 bell jars. And here's a picture of the vault, and you'll see that in the center is the international prototype of the kilogram, and these are others of the prototypes that were made by this company and serve as Czech standards. And this international prototype of the kilogram has been taken out of the vault only 3 times in its history, believe it or not, since 1889. Okay, so in 1889, the first CGPM meets. They confirmed that the metric system unit of length is the international prototype of the meter, and the unit of mass, the international prototype of the kilogram, and the signatories to the meter convention all received copies, these copies that this UK company had made. And US receives meter prototypes 21 and 27, and kilogram prototypes 4 and 20. And then numbers 27 and 4 actually become the US national prototypes of the meter and kilogram. And this is actually the picture of the US national prototype of the meter received in 1889. I have said nothing about the second. The second is actually not officially part of the metric system, but it had been defined in terms of the mean solar day for a number of years, and they just continued using the second. So we now have the meter, kilogram, and second, or MKS, which together provide mechanical units. In other words, mechanics is now taken care of because we have the meter, the kilogram, and the second. For example, then acceleration from simple equations of physics, the unit of the acceleration is the meter per second squared, unit of force, kilogram meter per second squared, etc. One interesting thing that's important for what I'm going to be saying is the watt. The watt can be realized mechanically or electrically. So consequently, that's something to keep in mind, as you'll see why. So keep that in mind. The watt is equal to the ampere. We'll talk about ampere times a volt. It's equal to the joule per second, which is the watt is energy per second time, and it's 1 kilogram meter squared per second cubed, whether it's realized electrically or mechanically. So that's an important point. You'll see why. Okay, so now we're looking about 71 years of progress, 1889 to 1960. Their national metrology institutes are created. For example, the National Bureau of Standards was created in 1901. In 1927, the CIPM creates consultative committees, or CCs, to provide technical advice and recommendations to them. And then they pass on any possible changes to the CGPM for approval. So today there are like 10 consultative committees covering all areas related to units, base units, time, mass, etc. Those people are mostly active scientists from the National Measurement Institutes. And they play a critical role in development of the SI. And there's one of the consultant committees called CCU, the Consultant Committee for Units, and they're involved with unit definitions. So, next decades are devoted to expanding the MKS, and there are 3 additions. The MKS then, don't forget, at this point is only involved with mechanical units. But obviously, life is improving. Electrical units become very important. Thermometric temperature and photometric, how the eye sees light. So they introduced 3 new units for electric current. They introduced ampere. For temperature, they introduced the Kelvin, and initially a degree Kelvin, but the degree was then subsequently dropped, and it's just called the Kelvin symbol K. And for photometric quantities, luminous intensity, the unit is candela. So we now have 6 units in the metric system. And in 1948, the 9th CGPM recommends creation of a single practical system of units of measurement suitable for adoption by all countries adhering to the meter convention. And the CIPM in 1956 says we ought to call this system the System International de Unité, International System of Units, as the name of the system envisioned by the 9th CGPM. So you can see there's a whole hierarchy, lots of activity in developing improved measurement in the metric system. A side comment, they add the ampere as the electric unit, a complicated decision that took many years to decide what electrical unit to add, and they just chose the ampere, and this ampere is actually defined in terms of the force between 2 current-carrying conductors. And I just wrote this equation. This equation defines this constant called the permeability of vacuum, mu0. So we have a force between 2 parallel conductors of, this is force per unit length. So force per meter, I1 and I2 are 1, D is 1, I1 and I2, 1 ampere, 2 parallel conductors carrying the same current. Distance between them is 1 meter, and so on. So mu0 turns out to be this number, 4 pi times 10 to the minus 7 Newton per ampere squared, the Newton being the unit of force. So this is a great advance because we now have all these other electric units. Having defined the ampere, we can then define the volt V for voltage, and again, these are just combinations of these 4 units, kilogram, meter, second, and ampere, and so on for these other electric units that some of you may be familiar with. The ohm, Tesla for magnetic field strength, and of course, again, mentioning the watt. Again, the watt, showing how the watt equals ampere times volt, and that reduces to the ampere times volt. Put the volt there, down here, and you get kilogram meter squared per second cubed. So again, the watt power, electric power and mechanical power are the same, no difference. Okay, 10th CGPM in 1994, they choose 273.16 Kelvin for the triple point of H2 of water to define the fixed point of the thermodynamic temperature scale. And they formally adopt the length, mass, time, electric current, and thermodynamic temperature, and luminous intensity as base quantities, and the units are then called base units. The meter, kilogram, second, ampere, Kelvin, candela are base units. So, 1956, the CIPM is requested by the 9th CGPM. In 1948, recommends the name System International de Unité be given to the practical system of units envisioned by the 9th CGPM. And so what happens its key is what happens in 1960 at the 11th CGPM. This is when the CI is actually officially created, the International System Units. And they define six kinds of quantities in the general sense: coil-based quantities, length, mass, time, electric current, thermodynamic temperature, and luminous intensity are base quantities. And then they choose 6 quantities, same kinds of quantities in the particular sense, called base units: the meter, the kilogram second, ampere, Kelvin, and candela. They also adopt 2 supplementary units: the rad and the stearadian, symbol SR, for measuring angle and solid angle. Give the definitions of the 6 base units. They introduce prefixes like giga and nano, 10 to the 9th or 10 to the minus 9, and adopt these 13 special names and symbols for each combination of base units called derived units: the Newton, joule, watt, volt, ohm, etc. So that really is the SI formally created, and at the same time they also redefine the meter and second. The meter now was defined in terms of the number of wavelengths of a particular radiation in the krypton atom, krypton 86 atom, and they refine the definition of the second in terms of the length of this fraction of the tropical year for 1900, etc. So we now have a new definition of the meter and second. Okay, so now we continue. Work continues to advance the SI. 13 CGPM, we define the second in terms of the frequency of the transition of the cesium atom. We added in a 7th base quantity called for the quantity amount of substance with base unit mole, and 1 mole is as many entities as there are atoms in 12 kilograms of carbon-12. So now we have physicochemical quantities and units are now added to the SI, so we now have the areas covered are mechanical, electrical, thermometric, physicochemical, and photometric. So we now those 7 areas now have units. And in 1983, the meter is redefined in terms of an exact value of the speed of light in a vacuum. I should add, why is all this activity happening? Why is so much work going on? And the whole idea is to create a system of units that can be realized by anyone, anywhere. In other words, one can envision that every country has a National Metrology Institute like NIST, MBS, NIST, and they, if they want to, can actually build apparatus to realize the units themselves, so they don't have to send things to the BIPM for calibration or anybody else. So that's sort of the focus of all this activity and work. So the work continues, 1960 to 2019, to focus to further improve definitions of the 7 SI Bay units with this idea in mind so that people, any lab can realize them. And the problem is with the kilogram. 21st CGPM 1999 recommends NMI's continue research as the artifact-based definition of the kilogram could be replaced by one based on a natural constant. So that's the big problem. You still have the kilogram defined as the mass of this platinum iridium hunk of metal sitting in a vault at the BIPM. As an aside, there are actually 2 ways to define units. One is called explicit unit, and that's sort of the traditional way. Unit is explicitly defined. That is, the quantity, the particular quantity chosen as the unit is defined. So like the meter is the length of the path. Length of the path, that's the length. So the meter is defined in a particular length, namely the path traveled by light in vacuum during this time interval. And again, recall a unit is just a particular example of a kind of quantity. So these definitions of units focus are all that way, but one can actually have a different version of the definition, because in each definition there is a reference constant. And one could actually then define the unit by simply saying this reference constant has this value. For example, one could say for the meter, the SI is the system of units in which the speed of light in a vacuum, C, is 299,792,458 meters per second. So you don't have to, so that is equivalent to defining the meter in the previous way, where you actually specify the particular example of the quantity length as a unit. So that's something to keep in mind. So down here we show what are the reference constants of these 7 SI-based units at this time. Well, for the meter, it's the speed of light. For the kilogram, it's the mass of the international prototype of the kilogram. For the second, it's the frequency of the cesium atom, hyperfine splitting. For the ampere, it's mu0, this magnetic constant. K is the triple point of water. The mole is the molar mass of carbon-12. It has an assigned fixed value. And for light, it's the candela. So these, okay, so let's see. What time, would you say? Oh, we have lots of time, okay. So, now we have to turn, how do we finally replace the kilogram? And that's a bit of a long story, and it's involved 2 Nobel Prize winners, etc. So, in 1962, a fellow by the name of Brian Josephson, who at the time was a graduate student in the UK, theoretically predicted the behavior of something that is called the Josephson junction. Josephson junction is 2 thin superconducting films separated by a thin insulating layer. And it turns out that if you irradiate such a device, Josephson junction, you can induce across this junction, when it's superconducting below its transition temperature, and radiate with microwaves, you can induce voltages across this device. And the frequency of the radiation, frequency F, is related by this equation to a constant called the Josephson constant. So the voltage N, these are steps. You must shine a microwaves on this device, you induce steps in their voltage. If you scan, pass a current and measure the voltage across the device, that's given by this equation, where N is an integer. F is its frequency and Kj is the Josephson constant, but the Josephson constant, believe it or not, is exactly 2e over h. E being the charge on the electron, positive, absolute value or charge on the proton, elementary charge 2e, and h is the Planck constant. So, what this device is a Josephson junction, is a voltage standard dependent only on E and H, since one can measure frequency very accurately. So this is a very important discovery of how to generate a voltage standard with, in terms of these fundamental constants and the measured frequency. So he won the Nobel Prize actually in 1973 for this discovery of the Josephson effect. And believe it or not, another effect, quantum effect, was discovered by Klaus von Klitzing in 1980, won the Physics Nobel Prize in 1985, and it's called the quantum Hall effect. Now, the Hall effect was something known for many years. It's described here. We have induced a voltage across an electrical conductor. And the conductor has a current flowing through it, IC, and applying magnetic field perpendicular to both the current and voltage. So that's called the Hall effect. But it turns out in certain devices, certain semiconductor devices, the Hall effect, the Hall voltage, is quantized. and the whole resistance is given by this equation. Rx, y, I won't explain why it's xy, equals the Hall voltage divided by the current. And that is quantized, this resistance is quantized and equal to h over NE squared, h Planck constant, E the element in charge, N an integer. So we now have a device, a quantum Hall effect device, is a resistance standard dependent only on E and H. So the third great invention is the Kibble balance. In 1975, a physicist at the National Physical Laboratory, which is the UK equivalent of NBS or NIST, invents an apparatus now called the Kibble balance. In his honor, after his death in 2016, it used to be called the Watt balance, because it enables a power P, unit watt, to be measured in both electrical and mechanical units. So this is a great advance. You actually can, using this apparatus, and the apparatus, I don't go into super detail, but there's two phases. There's a velocity mode. You move a coil at a velocity v at a magnetic field B, and you induce a voltage V equals VB in it. And then there's the weighing mode. This coil is in a magnetic field B, carries a current I, experience a force F equals IB, exactly which you balance by a gravitational force, a mass times the gravitational acceleration at the site of this apparatus. And then you eliminate B from these two equations, and lo and behold, you have this relationship. The mass in the weighing mode, that you use in the weighing mode, is equal to QHG over V. Q is a quantity that involves step numbers, the radiation frequencies that you use in the Josephson and quantum Hall measurements, well known. G, the acceleration due to gravity. You can measure that at the site of this apparatus. V, the velocity that you move the coil to. You can measure that very accurately. So, by the early 2000s, a Kibble balance could relate a 1 kilogram mass standard to the Planck constant H within a few parts in 10 to the 7th, few parts in 10 million. So this was a major breakthrough, obviously, and therefore the people started thinking about redefining the kilogram in terms of H, given serious thought. You know, can we improve this apparatus so that we can reduce the uncertainty, say, by 1 order of magnitude? General feeling was that if you can achieve a couple parts in 10 to the 8th, then you could proceed with getting rid of the kilogram and replace it with a definition based on H, and use the Watt balance, the Kibble balance, to realize a unit of mass. Here's and I'll get to this. We published a paper in 2005, a gang of 5. I'll talk about that a little bit. But here is what a Kibble balance looks like. This is the NIST-4 Kibble balance. And you see this wheel. This wheel is how you turn the wheel, and that moves the moving coil in the part of the experiment where you move the coil in the magnetic field. And give you a size of scale, here's the same picture, but here you can see a fellow here with the apparatus. So this is a pretty big apparatus. And this is the NPL apparatus, now, Kibble's original balance, actually, that was for various reasons transferred to the National Research Council, the equivalent of NBS in Canada. So this is a big, serious apparatus, as you can see. Okay, so final road to the new SI. We published a paper, the Gang of 5, we published this paper called Redefinition of the Kilogram, a Decision Whose Time Has Come. Because, and this group of people, I'll show a picture of us, got to be called the Gang of 5, because we got involved in pushing for this redefinition. And so the CIPM in the 94 meeting in late 2006, they adopted a recommendation on the preparatory steps towards redefining the kilogram, ampere, Kelvin, and mole so that they are linked to exact values of fundamental constants. And then we published another paper, 2006, and outline how one should do this redefinition of the kilogram, ampere, Kelvin, and mole, a proposed approach to the implementation of CIPM recommendation, this particular recommendation. So the bandwagon started. Everyone's really enthusiastic about this happening. And so in 2007, the 23rd CGPM outlines the work required so that these new definitions can be adopted and encourage its pursuit in all the National Metrology Institutes to continue this work. So a consensus is finally reached in the National Metrology Institutes, the consultative committees of the CIPM, and to proceed with the redefinition. And they also decided to use the explicit constant type of definition as the formal definition of the system of units. So 24 CGPM 2011, they agrees to this approach, hopes all required work will be accomplished by the time of the 25th CGPM in 2014. The 25th CGPM in 2014 concludes, although much work has been accomplished, the data do not yet appear to be sufficiently robust to proceed with adoption. So everyone's still working very hard, frantically, and all the National Measurement Institutes doing and making measurements of various kinds that will enable us to proceed with this redefinition. And I should say there's a committee called CODATA, Committee on Data for Science and Technology, which has a new, slightly different name. I won't bother with that. And the topical group and task group of this CODATA committee is called the Task Group of Fundamental Constants. And they have periodically, since their founding in 1969, generated sets of recommended values of the constants, something I've been involved in since 1969. So the TGFC is directed to analyze the existing data and come up with recommended values for the four constants, H, E, K, and N sub A. Again, H, the Planck constant, E, the elementary charge, K, the Boltzmann constant, and N sub A, the Avogadro constant. So we carried out a new adjustment based on the summer of 2017, based on all the data that were available by July 1st. We published then two papers. One paper, data analysis for the CODATA 2017 Special Fundamental Constants Adjustment, and the actual values in the second paper, parallel papers. And the reason that was possible to do, because new data had become available since the 2014 CGPM. So people actually had been able to achieve this goal of parts in 10 to the 8th uncertainty using a kilowatt balance to realize get the certainty of the mass measurement down to this level of few parts in 10 to the 8th. And they decided, the CGPM met in November 2018. They adopted this revised SI with a starting date of 20 May 2019, which is World Metrology Day. It honors the day in 1875 that this, the Treaty of the Meter, the Convention de Metre. That was signed in 1875, which started all of this. So that's why that date was chosen, to commemorate that signing. Here's a picture of the Gang of Five at the 26th CGPM. The CGPM unanimously agreed to go ahead with this redefinition, and we were there at the meeting in Versailles. The short one is me. And here we are having a toast after the signing. And this is the gang of 5. These are all my, unfortunately, Ian Mills has passed away since then, but the other 4 were alive and well and kicking. And here's the definition. So this is it. So the new SI was formally adopted, and this is its definition. The International System of Units, the SI, is a system of units in which these 7 quantities have these values. The unperturbed ground state, hyperfine transition frequency of the cesium-133 atom is this number, speed of light is this number, etc. So that is the new SI. Now, the BIPM we have publishes a book periodically defining the SI and discussing its history. And they actually then have in addition to this definition, they give other explanations of how the units, are derived from this definition. So people are not necessarily, don't necessarily have to say, what is this all about? How does this work? How does this actually define units? And I will say if anyone wants to know, they can look at this publication by the BIPM. It's online. So here it is, just a summary. So we have 7 units, 7 reference constants, and the second S, meter length L, kilogram, and so on. And one asks, I told you a very long story. How did it happen? 229 years of hard work. Literally hundreds, we're talking about hundreds of people, scientists, all this period of time working to improve the measurement system. So one might ask, what's going to happen in the future? We finished, and presently the effort is to improve the definition of the second. The second can actually now be realized, that current definition based on this transition in the cesium atom can be done with parts intended to the 16th uncertainty. But that frequency is in the gigahertz range, and one can now measure optical frequencies. Oh. So people are now working very hard to come up with another reference, a particular transition in another atom. Strontium, there's lots of candidates that might have an uncertainty of parts intended to the 18th or even parts intended to the 19th. So we have this potential. That's currently a big effort underway in national labs to see if we can adopt, and I would say in the next 5 years, probably we will adopt a new definition of the second that will be able to be realized within the certainty of, as I said, parts intended to the 18th. In fact, a paper is just published that shows the uncertainty was parts intended to 19th, 8 parts intended to 19th of just a new recent measurement. So I think that is the next big change that's going to happen. And of course, some people are always worried about how the candela measures how the eye perceives light, how bright things look. And so people are thinking about whether there can be some better way to define that unit. So anyway, work is continuing, and laboratories are building apparatus and trying to be able to realize units themselves. And I think I'll end there. And thank you for your attention.
one thing I wanted to say is that this has been a rare treat for all of us, that at many of these international meetings, Dr. Taylor represented the United States of America. He is our country's expert on the standards.
There are others too, as well as myself.
Well, but this is the man. So this is a chance to talk to the man. Please line up, and Mary Koch, go ahead.
This is a political question, but it's about the metric system. It seems that the United States and Liberia and Myanmar are the only 3 countries in the world that have not adopted the metric system. What's going on?
Well, I can answer that question very quickly. There has been an effort over the years, started in the early 70s, by people at NIST, wrote a document about how we should, I've forgotten the exact title, the time to change to the metric system, something of that sort. So we started doing that. We started giving some thought, and in fact, in the late 70s, there was actually an effort to change, but it died because I don't recall exactly why it died. Okay, I think it was people were troubled that they would have to change all kinds of measuring instruments, workers. And who's going to pay for that? People have to go out and buy all kinds of new measuring, memory tape measures and tools, et cetera, et cetera. And that was going to be expensive. Workers weren't going to be able to do that on their own, et cetera, et cetera. So it was an economic issue, as I recall. Then there's another big effort in '88. There was a law passed, the Competitiveness Act, that changed our name from MBS to NIST. And part of that was going to push for metrication. And in fact, we actually changed to A4 paper in the government at that time. And where various public works were done, used the metric system to be built that. So that was in like '88. But then in the election of '94, when Newt Gingrich got in, he said, this is an unfunded mandate, because the government was requiring states to change the signs, to build things using the metric system. So that was the goal, to stimulate the change in the metric system. But he said, hey, that's unfunded mandates, so they killed the whole program. And nothing has happened since 1995. And I don't see any possibility of change in the future. Not my lifetime. Yeah.
Wonderful talk, thank you. I have a chicken and egg question. How much of the advancement of the definitions used in these metrics came about because instruments were developed that were able to measure to higher precision levels? Or was it the physics that went before the devices were able to measure to that precision?
Well, the physics, there obviously a lot of work was done on the Josephson effect and the quantum Hall effect, theoretical work as well as experimental work, to prove that that really was 2e over h or h over e squared. So that was, that lasted for decades. I mean, the Josephson effect was, as I said, discovered in 61, was it? Yes. And the quantum Hall effect in 1980. So there's 20 years more than that of work, research, to demonstrate, looking at different materials and so on, to demonstrate that they were really invariants. So I would say the physics preceded the measurements, or at least they were in parallel. The measurements, people were doing measurements to verify the theory.
Thanks.
Sort of a related question. How close are we to running into limits of measurement that are imposed by the Heisenberg uncertainty principle, since some of the new definitions are based on quantum effects.
Oh, that's a good question. I really can't answer. I don't think we're anywhere near that limit.
I think this might be a repetition of the same chicken and egg, but I'd like the answer again. If you're defining the constants as something measured in meters or seconds or something like that, how do you get the definition? Which comes first? How can you measure it if you don't know what a meter is?
You fix, well, you fix the value. Well, take the meter. Okay, we fix the value of the speed of light. Okay, the speed of light is a certain number of meters per second. So we have that number. That's an exact number. Now, the second is defined by. No. That's the meter. That is, we fix this value of the speed of light is an exact number, a new number, and that defines the meter per second. And the definition of the second fixes the second, and you could take that second and combine it with the meter per second and get the meter. So that's how it works. So all those numbers are exact. No uncertainty. They are fixed numbers, and by fixing them, they define the units. But they all interact. In other words, it's a set. And you have to have this entire set of units and combine them as necessary to realize a particular unit.
I remember from taking physics in the 70s, that they had some of these definitions sounded familiar. I recall an ampere was a coulomb per second or something. They never suggested that those definitions were changing. If I had taken physics in the 50s, would they have had a different definition for all these things than they did for high school students, for college students in the 70s or in the 90s or now?
Well, physics, right, the ampere is still a coulomb per second. but that's not the definition. The definition at the time was an ampere was defined in terms of the force between current carrying conductors, and the fixed value of mu zero. So physics hasn't changed. In other words, all the physics relationships between quantities are still the same. Nothing has changed. It's only the units that have changed. Now, I should say, I didn't mention this. The certain constants were exact in the old system. Those constants are no longer exact. So we have a price, like the mu zero, the permeability of vacuum, mu zero, was exact, 4 pi times 10 to the minus 7, etc. Now it's an experimental quantity. You can't. It's not that exact. It's defined in terms of other fundamental constants that are not exactly known. So that changes from one least squares adjustment of the constants to the next. These there's three constants that have now no longer were previously exact or no longer exact. But because we have so many of these, all the other constants are now exact. A whole host of new constants that were not known exactly are now exact. So the trade-off was decided, it was advantageous. The fact that these other constants, mu zero was no longer exact, the molar mass of carbon-12 was no longer exact, that was a small price to pay for having all of these other constants being known as being exact. And as that, I can't say anything more than that. I mean, we really look at that. But that was a payoff. So in other words, it wasn't free. We did lose something, but we gained, its feeling was we gained so much more by doing this. For an example, now converting from, say, electron volts to kelvins, energy, those conversion factors are exact. The whole list of constants are now exact that were no longer exact, that were previously not exact. So it's a small price to pay. That was the point, to give up the exactness of these other constants to get all these new constants being exact.
The original constants that were set out, the bar and the weight for the kilogram, have any of these new ways of calculating that change the actual length that we attribute to a meter?
I'm just thinking about the kilogram. The meter bar has long been, has not been used for, decades. So I don't think anyone ever pays any attention to the original meter bars. The kilogram is different, though. So the question is, how consistent with this new definition? I mean, let me put it this way. As I said, there's a certain uncertainty in the Kibble balance, right, relating a mass to the Planck constant. And that uncertainty is comparable to this past uncertainty of the reproducibility of the kilogram. As I said, over the years, people have compared the kilogram, the International Prototype kilogram, with other kilograms, and you can look at them how they vary one to the other. So the feeling is that over the years, maybe the kilogram's mass has actually changed by 5 parts in 10 to the 8th, for example. And that is at the level, that 5 parts in 10 to the 8th is comparable to the uncertainty of what a Kibble balance can achieve. So the feeling is that the system is now, it's consistent. The past and present are consistent. But within that spread, though, not any better than that. I would say we can reproduce the kilogram to a few parts in 10 to the 8th, and that's it.
A meter is not a...
No, meter. The bar was limited, right? We now can. Let's see. I don't remember what the actual uncertainty of the the length. I mean, length. You have to worry about temperature. I'm just thinking about how accurately one can actually measure. I don't know off the top of my head, how accurate one can now measure the length of something like a meter. Don't know what that. Can't say off the top of my head how accurate that would be. Your best accuracy, say, for the length, if you wanted to establish the length of a meter in a laboratory, something to think about.
Thank you for your presentation and the clarity of it and the interesting and the work you've done to represent us at all these international conferences. Could you just say just a few words about what you mean by a constant being exact? I'm a mathematician, so when I think of exact, I have one idea in mind, no unending decimal. So what do you mean by constant being exact?
It's a sign. We pick a number. Right, we pick a number for the speed of light, right? We say the speed of light is this number. That's it, and it's exact. It's exact, right? Just those digits. That's it. The decimal stop. That's right. Okay, right.
I have a question there. When you say a kilogram, an accuracy to 10 to the 8th, can you give me a visual for that? Is that like how much would that be? A tiny little piece of dust? Or, I mean, trying to visualize it is very
That's a good question. How much is a couple parts in 10 to the 8th? That's a couple parts in 100 million. I don't really know. I don't really know what. Certainly, it's not a speck of dust. I think that's probably not the case. I don't know. I really don't know how. But as I said, they developed a technique for actually cleaning, a cleaning technique for cleaning these standard masses. But remember, the old definition was the mass of the international prototype of a kilogram, whatever that was. That is it, by definition. So if that mass changed, the kilogram changes, the unit changes, but it's that mass.
So Dr. Taylor has presented a mass of information. He's gone to great lengths, and he's shed some light on this issue. We ask you to go to the length of helping us by making our collection basket a little heavier, more than just, something in a 10 to the minus 8. And we look forward to seeing you all next week, and have a good day at Chautauqua. Thanks to Dr. Taylor.